It has lost energy. The dissipation is friction. And careful, the bounce is time reversal. If I make a movie and show it reversal in time, it's the same. But the actual phenomenon is not time reversal, right? If I show a movie that I let it go like there and then it bounces higher, you say, no, the movie, you're cheating me. It's the other way around, okay? So dissipative phenomena, friction, are not time reversal invariant. So I expect this to lose energy while it's going down into heat in the air, to lose energy while it's bouncing into heat in the ground and the ball itself, and to lose energy while it's coming up, so it doesn't come up all the way up. So similarly, I expect the black hole to dissipate while it's shrinking, dissipate all the time. So not coming up the same big black hole that it was before. So how does it dissipate? Well, we know how it's dissipating thanks to the best scientific result of Stephen Hawking, who was a visitor, this PI, more than once, who made a very convincing argument that if you leave a black hole there and you still wait from the outside, it's not staying forever, but it's dissipating, it's losing heat around and becoming smaller and smaller and smaller and smaller. So what is reasonable to expect is a black hole evolves into a white hole, but a white hole very teeny, because it's lost a lot of energy. Very teeny, the mouth, where is my black hole here? This becomes very teeny, but inside you have still this huge volume which has been bouncing and is coming out. How big? And here is again, loop quantum gravity gives a hint, because you see, a black hole can quantum jump into a white hole, but a white hole, this is something which is well known from classical general relativity, a white hole has a probability of falling back into a black hole, falling back into itself. It is unstable. So a black hole can do a white hole, a white hole can do a white hole. What happens? They transform each other and they end up sitting on the minimal energy, on the stable solution. This is what quantum mechanics tell us. When you have two states that can transform into one another and you let them stabilize, they sit on the minimal solution, which is a quantum combination of the two. So what the theory suggests is that after the black hole has become evaporated, become very small, what you get is a teeny, teeny thing with a big interior, which is a quantum superposition of black and white. The universe is fantastic. So how big? Well, once again, loop quantum gravity comes in, because the main prediction of loop quantum gravity is that geometry is discrete. So area can be 0 or can be one quantum of area, Planck area, nothing in between. Now, if you have this interior, it cannot be 0. But so the area goes down up to its minimal area. And the minimal area is one Planck area, but this is black hole, so there's a mass. The mass is given by the area, and the mass is going to be one Planck mass. Now, one Planck mass is what? Very big, very small. Do you know how much is a Planck mass? It's a microgram. It's my hair. Okay? That's exactly the mass. A centimeter of my hair is a Planck mass. So here we have a prediction. Once again, to which I believe firmly 2 days a week, that it's possible that the universe is full of these little things, which are remnants of black holes, okay, whose mass I know is a fraction of microgram. 0.14, it can be computed. Planck mass. And I'm going toward the end. Suppose this is true. I'm pretty confident this is true, especially on Monday and Tuesday. Could we detect these things? Could there be a lot of these things? Well, there is a fascinating possibility. Suppose that in the early universe, or even in some early phase before the Big Bang, a lot of black holes were produced and had time to become remnants. Remnants have a long, long life, not infinite, but long life. So suppose you have a lot of this little things, a microgram, a fraction of a microgram, very teeny, zooming around. Would we see them? Well, we would see like a powder, but we wouldn't see it because these have a mass but not a charge, not a magnetic charge, nor an electric charge. So we don't see them, okay? They're invisible, but they have weight, have mass. So there's gravitational force. So it would be like some sort of matter which is dark, but it's all over the universe. Sounds familiar? So quite astonishing, the astronomers have seen mysterious things, which is dark matter, they call it dark matter, which is something which only interact gravitationally and could very well be, as far as we see today, powder. And if you do a calculation how many there could be now one that zooms here and goes through, because it interacts very, very weakly, only gravitationally. Of course, there's a lot of if here. If low quantum gravity is right, if the scenario of the bounce is right, if there's enough black holes in the past that have become these things. There are other hypotheses about dark matter, many, none very convincing, in my opinion. This one has a characteristic that doesn't require any other physics except quantum mechanics and general relativity. No supersymmetry, many dimensional modification, Einstein equation, you name it, okay? Maybe. But if so, could we actually detect these things? Well, my last paper, I want to just take you all the way to the research I'm doing now. My last paper published is a few physical review letters come out in the fall. It's how to build a detector who actually would detect one of these very, very teeny hair that is flying by fast because we're moving through the dark matter. And we think that we have enough technology using quantum technology to actually build a detector of that. It's big, complicated, who knows. To see the gravitational waves of these things, somebody long ago said, let's build a detector. Took 30 years. Kip Thorne and his friend got the Nobel Prize for detecting the gravitational waves. So maybe this is, but wait, we are still inside the black hole, right? I said, we jumped to a white hole, now we have to come out. It's going to be hard. Your imagination has to be sharp, because you have to come out for very teeny, Planck-sized things, transform into radiation. So, okay, imagine we can, our consciousness somehow survive that. We're out. Last comment. We've gone in, I've taken you in, going through, so, horizon, falling in, through these things. It's called a singularity, but singularity is a stupid name. Singularity is what would happen if there's no quantum mechanics. And remember, singularity is not somewhere, it's not in a place, it's not down there at the center of black hole. It's a somewhen. It's when this shrinks around you. So you jump through the singularity, through this quantum process, which is not strange, because we are a quantum process jump all the time. We are jumping quantum process jump. We are in the white hole, and we come out. Now, last comment. How long does it take, the entire process? Easy. If the black hole was very big, it has to evaporate. For a big black hole to evaporate, we know from Hawking's calculation how long is billions and billions and billions of years. So, very, very long. But wait, time is different outside and inside. What about inside? If we jump in, okay, black hole like this one takes less than half hour to, once we cross the horizon, to be squeezed to get the quantum jump. And then half an hour after to come out. Okay? So the time of this lecture. We go in, we cross, we're out, but 1 hour. That's it. But in the meanwhile, the universe has evolved for billions and billions and billions of years. So that's possible last way of viewing this fabulous object here. A black hole is just a shortcut to the future. You jump in, it comes out 1 billion years later for the universe, and just half an hour for you. The universe is absolutely fabulous. Thank you very much. Thank you.
Thank you so much, Carlo, what a wonderful talk. All right, so now we have time to take some questions.